Hi, welcome back to the trigonometry lectures on educator.com. Today we're going to learn about the last trigonometric functions. We've already learned about sine and cosine and tangent and cotangent. Today we're going to learn about the secant and cosecant functions. So let's start with their definitions. The secant function is just defined by the secant of theta is 1 over the cosine of theta. And of course that only works when the cosine of theta is non-zero. And if cosine of theta is equal to 0, we just say the secant is undefined. And the cosecant function, which people shorten to CSC, is just 1 over sine of theta. And again, if the sine of theta is equal to 0, we just say that the cosecant is undefined. So let's start with the first example right away. We have to draw a graph of the secant function. And in particular, we have to label all zeros, maxes, mins, and asymptotes and figure out what the period of the secant function is. So remember now that the secant function, secant of theta, by definition is 1 over cosine of theta. So a really good place to start here when you're trying to understand secant theta is with the graph of cosine theta. So let me start with a graph of cosine of theta. There's pi, there's 2 pi, and I'm going to extend this out a bit, 3 pi, and negative pi. Now remember that the cosine function starts at 1, goes down to 0 at pi over 2, so there's pi over 2. Goes down to negative 1 at pi, comes back to 0 at 3 pi over 2, back up to 1 at 2 pi, and the period of cosine is 2 pi, so it's repeating itself after 2 pi. So I'm not drawing secant yet, I'm drawing cosine of x. Y equals cosine of x. So in black here, I've got, we'll call it theta, cosine of theta. Now I'm going to draw the secant function in red. So that means we're doing 1 over cosine of x, or 1 over cosine of theta. So in particular, 1 over 1 is 1, and then as the cosine goes down to 0, secant is 1 over cosine, so it goes up to infinity there. And it does the same thing on the other side. So secant looks like that. When the cosine is negative, when the cosine is negative 1, secant is negative 1, and when the cosine goes to 0, secant blows up, but since cosine is negative here, secant goes to negative infinity when the cosine is negative. And then when cosine is positive again, secant is positive again, going up to positive infinity on both ends there. So that's what the secant function looks like. While the cosine goes between negative 1 and 1, secant is just the reciprocal of that, so it goes from 1 up to infinity and from negative 1 down to negative infinity. So now I've got the secant graph in red. Let me label all the things we've been asked to label. First of all, the zeros. Well, the secant theta has no zeros because it never crosses the x-axis. So there are no zeros to label. Maxes, all local maxes of the secant function. Well, here's one down here at pi negative 1 is a local max. Minimum at 0, 1 is a local min. 2 pi 1 is a local min. And so on. It has a local min or a local max every pi units. So we've got the maxes and the mins. The asymptotes are the places where the secant blows up to infinity or drops down to negative infinity. And so that's an asymptote at negative pi over 2. And at pi over 2, we have an asymptote at pi over 2. And again at 3 pi over 2. And again at 5 pi over 2. So basically every pi units, we have an asymptote where the secant function blows up to infinity or drops down to negative infinity. Finally, what is the period of the secant function? Well, the secant function is really dependent on the cosine function, and the cosine function repeats itself once every 2 pi. The period of cosine is 2 pi. So the period of secant is also 2 pi. And you can see that from the graph. It starts repeating itself after a multiple of 2 pi. So that's what the graph of the secant function looks like. It kind of has these u's and then these upside down u's, really dependent on the cosine function, because the secant is just 1 over cosine theta. For the second example, we have to figure out some common values of secant and cosecant at the angles in the first quadrant, 0, pi over 6, pi over 4, pi over 3, and pi over 2. Now, these angles are probably so common that you really should have memorized the sine and cosine. So I'm going to start by writing down the sine and cosine of these values. I'm going to write them down both in degrees and radians because it's very important to be able to identify these common values either way. So I'll write down degrees, radians, I'll write down the cosine and the sine, and then the secant and cosecant of each one. So I'll make a nice chart here. The values we were given were 0, pi over 6, pi over 4, pi over 3, and pi over 2. In terms of degrees, that's 0, 30, 45, 60, and 90. Now, you really probably should have memorized the cosine and sine of these already, so you probably shouldn't even have to check a unit circle. But if you need to, go ahead and draw yourself a unit circle and then draw out those triangles in the first quadrant, and you'll be able to figure out the cosine and sine very quickly, as long as you remember the values of the 30, 60, 90 triangles and the 45, 45, 90 triangles. But in particular, the cosine and sine of 0 are 1 and 0. For a 30-degree angle, the cosine is root 3 over 2. Sine is 1/2. For a 45-degree angle, they're both root 2 over 2. For a 60-degree angle, they're just the opposite of what they were for 30, 1/2 and root 3 over 2. And for 90, they're just the opposite of what they were for 0, 0 and 1. Now the secant is just the reciprocal of cosine. It's just 1 over cosine. So I just take 1 over 1. 2 divided by root 3. If you rationalize that, you get 2 root 3 over 3. 2 divided by root 2 is just root 2. The reciprocal of 1/2 is 2. And now the reciprocal of 0 is undefined. So those are the secants of those common values. The cosecant is 1 over the sine, while 1 over 0 is undefined. 1 over 1/2 is 2. Reciprocal of root 2 over 2 is 2 divided by root 2, which again is root 2. And then 2 divided by root 3 rationalizes into 2 root 3 over 3. and then 1 over 1 is just 1. So I've been really trying to drill you on memorizing the values of sine and cosine. I don't think it's really worth memorizing the values of secant and cosecant. They don't come up as often as sine and cosine. And the key thing to remember is that secant theta is just 1 over cosine theta. And cosecant theta is just 1 over sine theta. So as long as you really have memorized the values of sine and cosine, you can always work out the values of secant and cosecant. So I don't think you need to memorize these values of secant and cosecant. It helps if you practice them, but it's not really worth memorizing them. As long as you know your sine and cosine really well, you can always work out secant and cosecant. The last thing this example asked is which other quadrants the secant and cosecant are positive? Well, let's go back and remember our little mnemonic here. All students take calculus. That's in quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So that tells us which of the common functions are positive in which quadrant. In the first quadrant, they're all positive. In the second quadrant, only sine. In the third quadrant, only tangent. And in the fourth quadrant, only cosine. So let's figure out what that means for secant and cosecant, secant and cosecant in each case. Well, in the first quadrant, they're both positive, so both sine and cosine are positive, so secant and cosecant are both positive. In the second quadrant, sine is positive, which means that secant is positive, but cosine is negative, so secant is negative. In the third quadrant, tangent is the only thing that's positive. Sine and cosine are both negative, so secant and cosecant are both negative. And finally, in the fourth quadrant, cosine is positive, so secant is positive. Sine is negative, so cosecant is negative. And so now we have a little chart that tells us which quadrant secant and cosecant are positive and negative in. Again, I don't think you really need to memorize this. As long as you remember very well where sine and cosine are positive and negative, you can always work out where secant and cosecant are positive and negative. For our next example, we're asked to find whether the secant and cosecant functions are odd, even, or neither. And so let's remember what the definition of odd and even are. Odd is where f of negative x is equal to negative f of x. And that also, by looking at the graph, you can identify odd functions. They have rotational symmetry around the origin. Even functions, f of negative x is equal to f of x. And they have mirror symmetry across the y-axis. Now let's look at secant of x. Secant of x, well, actually we have to look at secant of negative x to check whether it's odd or even. So secant of negative x, secant, remember, is 1 over cosine. 1 over cosine of negative x. Cosine's an even function, so this is just 1 over cosine of x, which is secant of x again. So secant x is even. Cosecant of x, well, cosecant of negative x, cosecant is 1 over sine, so that's 1 over sine of negative x. But sine's an odd function, so this is 1 over negative sine x, which is negative cosecant x. So cosecant is odd. So that was just a matter of checking the definitions of odd and even, plugging negative x into secant and cosecant and seeing what we came up with. We could also figure it out from the graphs if we remember what those look like. So secant, remember, let me draw cosine. Secant is 1 over cosine, so that was the one that looked like this. So that's secant x in red there. And if you look, it has mirror symmetry across the y-axis, which checks that secant of x is really an even function. Mirror symmetry across the y-axis. Cosecant of x, let me draw a quick graph of cosecant x. Remember, that's based on the graph of sine of x. So I'll start by drawing a graph of sine of x. And now I'll fill in a graph of cosecant x. It has asymptotes wherever sine is 0. So that's now a graph of cosecant of x. And clearly that does not have mirror symmetry across the y-axis, but it does have rotational symmetry around the origin. If you spun that around 180 degrees, it would look the same. So it does have rotational symmetry. And that confirms that, that cosecant is an odd function. So we'll try some more examples later. You should try working them out yourself, and then we'll work them out together.